Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about maximum likelihood estimation for continuous models. Our goal is to learn how to fit continuous parametric models using maximum likelihood estimation. The prerequisites are a probability density function and also the exponential and Gaussian distributions, which are the two continuous parametric models that we have described in a previous video. Okay, so imagine that we have some data and we want to model them as being exponentially distributed or Gaussian distributed. In that case, we have designed, or maybe we have chosen, is a better word, a PDF f that depends on some parameters. The parameters theta, in the case of the exponential, will be this parameter lambda, which is kind of the rate, which is called the rate parameter. In the case of the Gaussian, it's the mean and standard deviation parameters, which we had denoted by mu and sigma. So let's see what we could do if we had a single data point, even though that's a very idealized situation and it wouldn't be very useful because you're not going to get a very good parameter estimate of a single data point, but it's instructive to see what you would do in that case. In that case, f of theta is a probability density at A. Okay, because when we plug anything in here, we have the density of probability at A according to the parametric distribution. But here we're going to do a change of perspective like the one we did when we were explaining maximum likelihood for discrete models. Instead of interpreting this as a function of A, which tells us the density at A, we're going to fix the data. We're going to say, okay, this argument is going to be fixed because we observe what we observe. And now we're going to vary theta. So we're going to interpret this object, which is the density under the parametric model at A, as a function of the parameters. So now how do we choose the parameters? Maybe let me draw a simple picture. So here let's assume that we have a single data point, which happens to be here. And now we want to fit a Gaussian to it. So let's see if I can draw a Gaussian. My drawing skills are extremely terrible. Okay, so that's a Gaussian. And the Gaussian has this parameter mu and another parameter sigma. Okay, so now we can vary the parameter sigma and mu so that the density at A, let me annotate, actually I should annotate it in the same color, right? So that is A, and this value here is f of theta at A. And as I vary mu and sigma, I'm going to obtain different values of the density. So if I, for example, I take mu all over here, the f of theta at A is going to be like that. So in general, for continuous, and let's assume that these two things integrate to one, they don't really look like they should integrate to the same thing, but I'm sorry, but I'm no artist. Okay, so which one would you choose? If you had to choose just between these two guys, between the pink distribution and the red distribution, I tell you, okay, I see only this data point. Which of these two distributions do you think generated it? Well, we know that in general, when we sample from a distribution, the density tells us where most of the samples are going to be. So most of the samples for this distribution are going to be here for this PDF. Most of the samples for this PDF are going to be here. Since our data point is there, we would probably say, I think it's the red one. Because of this, based on the same argument, on the same reasoning, it seems to make sense to choose the parameter that maximizes the density where we're seeing the data. Okay, so that's essentially what we're going to do. We want to maximize the density at the observed data points, but I've shown you an example where we have a single data point, right? And now we have to worry about what happens if we have more data. Okay, so in order to incorporate, in order to generalize this reasoning to more data points, we're going to introduce the concept of independent identically distributed random variables for the continuous case. If you remember, we already explained this for the discrete case. So if we have n random variables, a1 to an, these random variables are identically distributed if they have the same PDF. If you look at them individually and you look at their densities, if their density functions are all the same, then they're identically distributed. This is an assumption that makes sense for our data, because if we're fitting a distribution, the data points hopefully will each have the same distribution. Otherwise, what are we doing here? The second assumption is a bit trickier to define. We say that these random variables are independent if any set of n events, the first of which involves a1, the second of which involves a2, and so on up to an, if those events are always mutually independent, no matter how we choose those events. So, for example, we could say a1 is between 0 and 0.3, a2 is greater than 5, and so on and so forth. Those kinds of events, if I take n of them, they're always going to be mutually, and if I take any of them and they're always mutually independent, then we say that those random variables are independent. We're going to talk much more about independence of random variables later on in the course, but we just need to define this here in order to be able to define the likelihood. When these two assumptions hold for n random variables, we say that the random variables are IID, and we often model our observed data as IID. Okay, so now if we have some data points x1 to xn, and we assume that they are IID, then their joint density, we haven't defined what the joint density is yet, and we will do this formally a bit later on in the course, but for now you're going to have to bear with me. We're going to call the joint density, which you can just think of it intuitively as a generalization of the 1D density. So if you have two random variables, A and B, you can imagine that their joint density, I'm plotting just some contours, it would tell you, where you're more likely to see the two random variables. So in this case, maybe if you imagine that the contours are growing like a mountain, then maybe you would have more density here. This is just to give you like a very, very quick intuition of what a joint density would look like. Again, we're going to talk a lot more about it later on. So it just so happens that if the random variables are independent and they have the same individual densities, then the joint density is just going to be the product of the individual densities. For the PMF, this was easier to see, right? Because the PMFs are probabilities, so under independence, the joint probability, which was just the intersection of all the probabilities corresponding to each individual random variable, they just factored into the product of the probabilities. These are densities, so it's not immediate. Again, we're going to talk more about it later on, but for now we will just say that when random variables are IID, their joint density is going to factorize into their individual densities. And because we're saying that they're identically distributed, that's the assumption that we make when we're trying to estimate this parametric PDF from data. Because we're saying they're identically distributed, we're using the same function here. Okay, so we call the likelihood of a continuous model with respect to these n data points, the density at the data points, as a function of theta, because just as in the case of the individual data point that I just described, here we're going to fix the data, and we're going to ask ourselves, how could I tweak the parameter theta to get the highest possible density at the observed data? Here, because we're multiplying densities with each other, and densities can be larger than 1, but they often are not, the number here can actually become extremely small numerically. It could also explode, by the way, if the f's are larger than 1. So because of this, we usually put a logarithm in front for numerical stability, and we talk about the log likelihood, exactly as we did in the case of the discrete likelihood function. Given that I brought up the discrete likelihood function, this is exactly the same expression, except that we are replacing the density, the probabilities, the PMFs, by densities. Otherwise, we're going to do exactly the same thing. We're going to maximize this quantity with respect to the parameters that we want to fit to the data. All right, so as I said, that was the likelihood and the log likelihood. If we want to estimate some parameters using maximum likelihood, what we do is we maximize the likelihood, or equivalently the log likelihood. This is equivalent because the logarithm is a monotone function. Okay, so let's take a look at exponential models. Remember that the PDF of an exponential with parameter lambda is equal to this, lambda exponential of e minus lambda t when t is greater than 0. Usually we apply this model to data that are all non-negative. Okay, so let's derive the maximum likelihood estimator for the exponential distribution. First, we write down the log likelihood, so we have to plug in the PDF there. We plug it in, we get this. Remember that we have to put the data points, the actual data points that we observe there. Now we have a sum of log lambda exponential of minus lambda xi. This splits into, because the logarithm of the product is the sum of the logarithms, have the logarithm of the first term, which is just log lambda. The logarithm of the second term is just minus lambda xi. And now we have this sum. Okay, so the first term, they're all the same. So we have n log lambda minus lambda times the sum. That is the log likelihood of the exponential model. In order to plot it, we have to assume some value for the data. And this here, what I'm plugging in is the value of the data that I used for the call center example that we used when we explained the exponential distribution. Just so that you see how the log likelihood looks like. It's nice that it looks concave. It has this shape like this, so that there's a maximum, in particular here. And here I'm showing you 3 values. And remember that for any value here, we have a different fit to the data. So now let's take a look at the fit that we would obtain with these 2 values, which have a likelihood that is lower than this maximum here. For lambda equals to 10 to the minus 3, we get this value. Lambda is very small, so the shape of the PDF here does not decay quickly enough to fit the data well. Here, lambda is too large, the PDF decays very quickly, so that it doesn't account for this data very well. How do we find the best lambda? Okay, we can look at the graph, but how do you know which one is where exactly is the maximum of the graph? We use derivatives. The first derivative of the log likelihood is equal to, and remember that the derivatives are with respect to lambda, which is the parameter that we want to fit. The first term is easy, it's just n over lambda, and the second one is even easier, it's just minus the sum, right? We're going to take the second derivative to see what the shape of the function is. This is always a good idea to make sure that to determine whether you actually have a single maximum, or you have to be careful and there's perhaps other values of the parameters that would be equally good, or you have some local maxima and so on. If I take the second derivative, this is just minus n over lambda squared. This is always negative, which means indeed that the function is concave like that. We're going to have a single maximum. How do we find the single maximum? We set this guy to 0, so lambda is just going to be equal to 1 over the sum of the data. 1 over the average of the data, right? Because we have this 1 over n over there. Okay, so that's actually the rate parameter in this case, corresponds to 1 over the average of all the data points that we observe. We will see later on that this makes a lot of sense. Okay, so this is the value of the parameter in this case, the maximum, which again is obtained in a very simple way. Just set lambda to 1 over the average. And this is the fit that we get. You might be somewhat surprised that the fit here is actually really bad. This is because the data are not well explained by an exponential model at that point. There are many interarrival times that are very, very short, and that is not consistent with the values of the remaining inter-arrival times. So the assumptions that we made when we derived the exponential models don't hold exactly for this data. Okay, but this is the value of lambda that manages to fit the data well. And you can see this in two ways, right? Like, you're not being able to fit this. That may be good if you think that's spurious structure that you don't want to learn in your model, or that's bad if it is actually useful structure that is going to allow you to, for example, predict future inter-arrival times better. This will depend on the situation. Data science is messy. Okay, now let's move on to the Gaussian. The main difference between the Gaussian and the exponential for our purposes is that the Gaussian has two parameters, and this happens sometimes in practice, so it's good to know what we should do in those cases. This is the shape of the Gaussian. Remember that the mean parameter mu essentially tells you where the Gaussian is centered, whereas the sigma parameter tells you how fat or thin the Gaussian is. Okay, so let's do the same thing that we did for the exponential. First, we derive the log likelihood. Realize that now the log likelihood depends on two parameters. So we just plug in the PDF of the Gaussian there. We take the log. Since we have an exponential here, it's going to be easy to take the logs. The product splits up, so this part goes here. This part goes here. Actually, this part goes here, is what I should have said. Okay, we have all of these, all of these different terms. We can plot the log likelihood. Now when we plot it, we have two parameters, right? So we're gonna have to plot it as a heat map or a contour map in 2D. Okay, and this is how it looks like. Have parameter mu, parameter sigma. For example, for mu equals to 175 and sigma equals to 7.5, the value of the log likelihood would be, well, something close to minus 10,000. Okay. So now, as in the case of the exponential, we're going to show the kind of fits that correspond to different values of mu and sigma, in particular this point and this point. Okay, so here mu is equal to 174 and sigma is equal to 9. Yeah, I nailed it. The mu is too small. You can see this because the center of the distribution, the center of the fit does not align with the center of the histogram of the data. And the sigma might be a bit too large. You see this because the PDF seems fatter than the histogram. Okay, so yes. Okay, so the sigma is too large. We're above this very good point that we will see is the best point, and mu is to the left. Okay, what about the other point? Well, this point here, the opposite is going to happen, right? Mu should be too much to the right, and sigma should be too small, so probably too thin with respect to the data. But let's see how that looks like. Indeed, sigma is thin, and mu is a bit too much to the right, so the fit is not great. So how do we find a good fit so that the Gaussian curve is on top of the observed histogram of the observed data? We compute the log likelihood, and now we're going to differentiate it with respect to the two parameters in order to find the maximum. So with respect to mu, we don't have to worry about this term, we don't have to worry about this term, we only have to worry about this term. Okay, and because we know how to differentiate a square, this is going to be easy. It's just going to be 2 times xi minus mu divided by 2 sigma squared, and then we're going to sum all of those. Okay, so, right. Oh, and this 2 cancels out with this other 2. Okay, so we have that expression for the derivative with respect to mu. We take the derivative with respect to sigma. This part is just going to be n over sigma, and this part is going to be whatever is above divided by 2 and then times minus 1 over sigma cubed. Okay, and then we have this other minus in front. So the derivative is going to be equal to that. Okay, so now we could just set these things to 0 and this would give us an extremum of the function, or well, not necessarily an extremum, it could also be a saddle point, but we have to be careful, right? Because functions in 2D can have very different shapes. We're not going to, like this is multivariate calculus. You can go check it out if you want, but just very basically, here we're fine because we have actually plotted the function, and we see that basically this is a mountain that is coming up, 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 up. Realize the numbers are negative, okay, and all these counter lines are coming up like a mountain, so there's going to be a single maximum. How do we prove that mathematically? The way you prove that mathematically is by computing the second derivatives and the cross derivatives of the log likelihood, building the Hessian matrix, and establishing that its eigenvalues are negative. Okay, that means that this surface is going to be like an inverted bowl. It's going to be concave. You should look into some multivariate calculus if you're interested in that. For the purpose of this course, we're not really going to go very deeply into those considerations. Here, we plotted it, we saw that it was concave. We're just going to set the partial derivatives to 0 to find the maximum. When we set the partial derivatives to 0, this, it's pretty easy to do. Here we set this to 0. Immediately we see that mu is equal to, mu is going to be equal to, 1 over n, the sum of the xi's. Now I ask myself why, oh yes, okay, sorry. I always make this mistake. I'm gonna write it out because I was getting confused myself here. This would be xi over sigma squared minus n mu, right? Because we have to add the mu n times, that's where the n comes from. I was like looking at this and saying, well, where does the n come from? Okay, so it comes from there. So the mu is just going to be the average of the data. Now we're going to take that mu, I'm going to plug it in and set this to 0 once we have plugged in this value for mu. And what we get is xi minus mu ml, which is this sum, squared divided by n. We will see that's the square, okay? That's how we, so the value of sigma is the square root of this. It was just easier to show the square here. That is called the the sample variance of the data. And we're going to talk much more about it later on. But basically, how did we obtain it? We plugged in the value of the ML estimator for mu, and then we set this thing to 0. Okay, that's how we obtained it. Okay, so this is how we find this point here that is at the top of the mountain, and it gives us a pretty awesome fit. Okay. What have we learned? We have learned how to fit the parameters of continuous models using maximum likelihood. Thank you very much.